Yeah, thanks. Okay, thanks, Nana, for the invitation. I'll be honored to give the first talk in this workshop. So I will present you some work has been done with actually. So Chen Chu is actually a local high school student when we start the project, and then we joined the force with Gabriel and Matt during the KITP workshop 2 years ago, and then we're preparing some new results that hopefully we will finish hopefully this week, but we'll see. So things, well, there are some incidents, but I think things will get better now. Okay, so I want to basically tell you something that we explore from the phenomenological side by applying the causality condition that recently derived by George and their companies. Okay, so since this is the first talk, I will give you some brief introduction about phenomenology in heavy ions and give you some reason that why relativist heavy ion collisions is important as a workhorse to describe the dynamics of heavy ion collisions. So in heavy ion collisions, you can see that as things evolve, you will go through multiple stages of the evolutions where physics is governed by different length scales. So at the initial time, you have two heavy ion nuclei accelerate to really high velocities, and then they collide, and then you can system will go through some pre-equilibrium stage, about through 1 Fermi over C, reach some microscopic near equilibrium stage that you can describe system microscopically through fluid dynamics. And this evidence is through the experimental measurement that hydro really works really precise as effective theory to describe the dynamics evolutions in the coagulum plasma down to hadron Lorentz gas. And then when in this dilute hadron phase, the system density becomes low, and then you need to usually switch to the transport approach to describe hadrons dynamics microscopically, and then eventually they freeze out and fly to the detectors. The challenge in heavy ion physics is that all the interesting physics happens in a really short time scale, about 10 to the minus 23 seconds, or say yoctoseconds. And also the system is really small on the size of nucleus. So it's put very extreme challenge for the experiments to actually detect directly the dynamics happening in this early phase where coagulum plasma exists. So what relies on is really rely on trying to rewind the experimental measurements from detectors through some phenomenological dynamical model to early stage and infer the information from there. So that's kind of the way that we can extract information about, say, the property of coagulum plasma through the experimental data. And since we have a variety of species of hadrons and also other probes like ENM probes radiate from the collisions, really we can look at all of them together, which can bring us different aspects of information. And then using combined analysis, we will gain a lot of information about the property of QGP in the early phase. So I think the main goals, at least in phenomenology, is trying to constrain the property of the hot dense nuclear matter in this confined phase. Especially on the theory side, we are interested in about the equation state about this coagulum plasma and also its transport properties, say shear bulk viscosities, charge diffusions, and also kind of momentum exchange with real probes. On the experimental side, you can actually relate sort of kind of observable that have a strong sensitivity to these aspects. Ideally, you would expect that if we have one-to-one mapping, this can be solved easily by just measuring certain observables and then using the phenomenology model to constrain certain transport properties. However, in reality, this mapping is really complex. Multiple components on my QGP properties in my modeling affect all different kinds of observables. Or you measure, on the other hand, if you measure all these type of observables and you can treat this complex mapping, you can constrain these observables at the same time. And this become a generic inverse problem for our field to constrain, use a large collection variety of experimental data to deduce the property of coagulum plasma. And this inverse problem usually requires us to do a lot of high performance computing on the exascale and use the advanced statistical methods, so such as Bayesian analysis, to basically solve this inverse problem in a systematic way. So one of the current state of art can be done, this analysis is done by the GSK collaborations, and also there's other collaboration work over the years. You can see that the first Bayesian analysis start almost around 2015, and over the 10 years, people actually refine such approach and then use more and more data to constrain the observables. So for example, in GSK collaboration around 2020s, what we conduct is trying to use both RIC and LC energies, measurements, particle yield, mean PT, and V2, V3, V4 to constrain the theoretical model and deduce the property like shear viscosity of the QGP. So here, the gray band indicate the prior region in 90% confidence interval. After applying the constraint from data, you can see the 90% posterior indicated as the orange line band here. So what you find is that if you look at the hadronic observables, they actually can impose constraints on the shear viscosity near the temperature region from 115 to 125 GeV. Near the phase transition regions, you get the largest reduction for the phase space from the gray to the orange, and you also have some constraint on the ball viscosity in near the freeze out. However, in the high temperature phase, we don't really have any constraints using these hadronic observables in this case. Similar result also get also from the trajectory framework, also similar to this. So the question I want to ask is basically, in this case, is saying that in these calibrations, we usually use this so-called kind of bread and butter observables from the experiments, and we want to know, for example, if we impose the nonlinear causality conditions, what will be changed in this thing, what was the influence in there, and how it influence will be propagated to this Bayesian analysis in there. So that's the kind of the main questions I want to kind of estimate or answer through my talk. So let me basically give a little bit about kind of the setup of this multi-stage approach in heavy-ion collisions. So the main evolution has usually separated into 3 stages. So we have initial stage, which is basically pure, really far from equilibrium, and we have some usually can be use some pre-equilibrium dynamics like effective kinetic theory to drive the energy moment tensor to somewhere you can close to the hydrodynamic form. And then you perform so-called Landau matching conditions where you pose the underlying equation state to map the energy density from equilibrium stage to a hydrodynamic form with a kind of also of equilibrium components inside. Then you can evolve the T mu nu of the system through hydrodynamic equations on the order 1 Fermi over C of the evolutions to about 10 Fermi over C, where system become dilute, and you convert the energy moment tensor of the hydro to particle degrees of freedom, use so-called Cooper-Frye particleizations. So here, if you use the ideal, the T mu nu is ideal, the particleization is kind of well-defined with equilibrium distributions, and if there is viscous corrections, then Cooper-Frye has many different ways to kind of infinite number of ways to deduce delta F, which can match to the first order of the viscous tensor. But the idea is that we basically want to match the energy moment tensor from the fluid dynamic degrees of freedom into particles and then further propagate through hadron transport in the dilute phase. So the main idea is that at least through this multi-stage evolutions, we want to continuously evolve is the system's energy moment tensor from different stages, although that you would have some abrupt changes when you match the two theory, for example. The equation state usually is discontinuous when you match from pre-equilibrium stage to the hydro, because usually the effective kinetic theory is solved in the conformal limit, where equation state is a ideal gas equation state. So although the T mu nu may be continuous, you may still have some thermodynamic variables to be discontinuous during the matching stage. And this actually will actually make difference as we look at the phenomenologies. So one of the that surprising things in our field is that the hydrodynamics proved to be really work well in the large system, for example, the collisions, as you can see by carrying out this Bayesian analysis. However, hydrodynamic behavior is also found in the smaller system as even you go down to proton-led or proton-proton collisions. And seems to be that you can actually describe all these systems using hydrodynamics. But we want to see that how does this small system trying to push the limit of this application of the conventional hydrodynamic or this multi-state framework. So as example, for example, if you start with central lead-lead collisions, this is typical size of lead-lead collisions. Here, this is about 2 Fermi scale. You can see this is a so-called large system in our case. And you can apply hydrodynamics, and then you can see that you can describe the flow coefficients rather well as a function of charge multiplicities through the measurement, through the collisions. And then you can go down to some intermediate size, so you can say xenon-xenon collisions, which has about 40% less number of nucleons in the systems, and the system become a little bit smaller. You can use the same hydro and then get a similar quality of debridement on the anisotropic flow. And then you can even go to proton lead, which is this indicated as blue lines, and with the blue line theory calculations, and you can see that still hydrodynamic work reasonably compared with experimental data. The emphasis is that all these different systems is using one single parameterization for the theoretical shear viscosity and bulk viscosity. So there's no additional parameter when you go from this large systems to small systems. All of them are kind of consistently described in one unified framework. So this is basically what people usually call this the surprising effectiveness of hydrodynamics as you reduce the system size even to, say, proton-like collisions with only, say, about tens or 100 particles per unit of rapidities. And this is really kind of the regions we want to understand why hydrodynamic works for these small systems, and then what is the limit in there, and how does the fundamental conditions work in these small systems. Okay, so that's basically the phenomenology I want to kind of start, and then try to go into discuss about the causality conditions that usually people propose in this hydro framework. So let me start with basically what usually people start to impose on the transport bound on the transport coefficients. So this is usually derived a long time ago, I think in 1980s, that you can choose the bounds. There are some bounds on the coefficients of the second order transport coefficients. For example, if you write down the relaxation time of the shear and bulk viscosity, these coefficients cannot be arbitrary, small, and there needs to be some kind of minimum values derived from the underlying microscopic theory. For example, for shear, you can derive the C eta. Usually is about 2.6 to 7, depending on whether it's a strongly coupled or weakly coupled theory. And then zeta is similar for the bulk viscosities. And then in the equilibriums, you can derive some perturbation. You can look at the small perturbations of equilibrium fluid and derive these conditions to ensure that the propagation of the signal is less than speed of sound, speed of light. And then this is the condition you would get for these transport coefficients. So basically, the conventional one that use from the, say, microscopic theory, like transport, are basically this first choice of C theta 1 derived from Gabriel. That if you plug in this, you can see that this is a parabolic condition depending on the speed of sound in these conditions. And then you need to make sure that this expression is between 0 and 1 in order to not violate causality, even when the system is, the fluid cells in near equilibrium. So as you can see that even with the choice, so this choice, particular choice in this formula, this 14.55 is coming from the kinetic theory derivation in the small mass limit. And it's okay for the theory if the speed of sound is not below, say, 0.13 in there. So if we below 0.13, this even the case that this choice of the bulk viscosity will violate causality. Luckily, that if you use the equation state from lattice, the minimum of the speed of sound square is about 0.15. So that if you use the lattice Hawk QCD equation state, this is still okay. So the other choice from the, say, the strongly coupled case, that is can be dependent only on the 1/3 minus square linearly instead of quadratic form. And then you can actually allow for a kind of a larger regions for the causality. So So the static conditions can be valid for all different speed of sound, even go to 0 in this choice. Yeah. Yeah, so if you just have a fluid, so if you just have a fluid in the box static in thermal equilibrium, you introduce a small perturbations and look at the signal propagating these small perturbations, you can derive these conditions that that this needs to be between 0 and 1 for the speed of propagation to be below speed of light. No, just from the hydrodynamic equation motion. If you just do perturbation on the hydro equations, you can look at the modes like in different momentum space, and then you yeah. So this actual value derived from the macroscopic theory, like from a couple theory or from like Boltzmann equations. Okay, yeah. Yeah, it is perturbed in so from 7 usually it's from perturbed number from like Boltzmann equations. And then 2.7, I think, is from like ADS CFT calculation, but you get roughly this kind of values. Yeah. So the conventional value for eta is usually taken as a function as roughly value of 5, but you can, you have another question. Yeah. Mm-hmm. Yes, yeah. So if you kind of derive near conformal limit, so in the conformal limit, you see this is okay. But if you just use that value with the lattice equations in practice, like phenomenology simulations, you kind of really close to the boundary causality when the speed of sound is near 0.15. So I'm not saying that this is something ideally to be chosen, but this is usually chosen in the phenomenological simulation that you've seen before. So you can for sure you can vary these values, but we vary this value later. But you can see the effects on the phenomenology effect later. Yeah. Mm-hmm. Yeah. Yeah. Mm-hmm. 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 Yeah. Mm-hmm. Yes. Yes. Yeah. So 2 point something, right? Smaller. Yeah. Then I think this will be. Yeah. Mhm. I don't remember whether it go up or not, but probably will go up. Yeah. It go even safer. Yeah. Okay. Yeah. Yeah. Anyway, so that's kind of the static case. So yeah, so this is just a kind of describe. So if you plot the CS square for lattice QCD, the function temperature. So below these yellow regions is where we usually transit hydro to hadronic transport. So usually kind of focus on the area above the yellow regions. You can see that there's a dip of CS square near phase transition region in the lattice QCD about 0.15, which is somewhere here, which saying that if you use the blue line parameterizations, even in the static case where the fluid is in perfect equilibrium, you're really close to the boundary of the causalities. So there's little room left over for the off equilibrium causality conditions to get in here. And usually, if you use the transport coefficient choice, like shear viscosity equal to some effective number around 0.12, and ball viscosity has certain shape like this, which is used actually in the previous fit for the anisotropic flow. And you can deduce the value of tau pi, which is about 0.5 Fermi over C for the shear, and then similar value of the peak of ball viscosity relaxation time in these regions. The idea is that if you can increase the ball viscosity relaxation time longer, you can even also give a little bit bigger room for the causality to valid even the fluid is out of equilibrium. But this is kind of the standard fit to the experimental data with these parameters. Okay, so now we're going to go one step. So even before the full causality conditions derived by kind of George Veronia and his collaborators, they first initially, like in around 2019, look at the box sector and trying to include essentially a non-zero bulk viscosity in the hydro equation of motion, then derive the causality condition bounds, non-linear causality bounds with the presence of non-zero bulk pressure. So this is what we put into practice. So basically, this is a histogram of gold or p-gold collisions of basically evaluate this quantity at every fluid cell using the lattice QCD equation state. And the causality violation were basically in this gray area. So you can see that for 200, for gold inserted to 40%, which is relatively larger system, all the fluid cells are peak around, say, 0.6. So which is still valid, have the valid causal condition. And then if you compare with the small system of proton gold, you can see there is a histogram of the tail extending to a higher value, closer to the causality bounds. So these already tell you that in the small system where the pressure is large, you're also pushing the hydrodynamics closer to its causality limits. On the second plot, yes, yeah. Yes. So no. So the evolution had both shear and bulk, but during that time, George and the company only derived the condition for bulk. So there's extra things in principle for shear needs to be taken into account, which I will show in the previous slides. Yeah. So this is only during that time. This is only available, but I will show you in the next slides that you have bulk and both bulk and shear how it looks like. Yeah. Yes. What do you mean adding more stuff? Yeah. Mm-hmm. Yeah, it will make things worse. Always worse. Yes, yes. If the initial pi mean is large from the pre-flow, they will make things worse. Yeah. This is a non-linear part only for the bulk. But still, there is, yeah, this for sure, because for shear, there's always one large eigenvalue for the positive side and one large negative, because shear stress is traceless. So you always have both components there become large. So both ends will, yeah, so one gets better and one gets worse. Yeah, yeah. Yeah, so I will show you. I will show you that later on. Yeah. No, the shear is always coming. The shear tensor always coming. One eigenvalue is negative large and one positive large. So both either of them will basically give you violation causality. One you will improve the situation, but the other will violate, or you get the other way around. But I will show you exactly numerically. Yeah, agree. Yeah, actual case, yes. But I will see that in general, you will get always pushing the limit. Yes, yeah. It's not always for everyone, but yeah. Okay, yes, it's not that rigorous. Practical, everything looks, yeah. Well, you are practically will see most of the case you'll get worse. Yeah. Yeah. So typically, if you go to more central, this will shift a little bit to the smaller value. If you go to more peripheral, go like more like proton net, proton gold. Yeah. Okay, so even with these simulations, you also still start to see non-comfortable things in the simulation. For example, if you look at the value of bulk viscosity with respect to thermal pressure at every fluid cell, you can see that most of the bulk pressure in the GOGO case is actually below 1. So it means that the bulk correction is less than thermal pressure. But if you look at the proton gold, you can see that there's already kind of significant fluid cell at you get larger negative bulk viscous pressure, which is even larger than the thermal pressure. And then this is usually understood as maybe a metal stable phase where you could have cavitation built up in this case. But this is somewhere already you noted that they're not very comfortable in the simulations. Yeah. I think this is one that not in, I think part one, I'm not exactly remember, but there may be a small peak here that it might. initialize the bulk to 0. Yeah, that's the two situations. This is kind of a long time ago. I don't remember exact setup, but just to tell you that this is kind of where I guess the beginning when Georgia and their collaborator introduced these causality conditions, we do start to see this worrisome signatures, and then we worry also about how does this propagate to final state observables, and when we want to interpret the phenomenology side. For example, you can see that here we basically do exercise because of this worrisome, we look at say, okay, go-go system for V to the function PT, also proton go to V to the function PT. So if you remove those negative pressure, you can see that for proton go, it go from the black to the red. So it's a very sizable effect if you want to constrain, say that the bulk viscosity is always smaller than thermal pressure. So there is a visible effect in the small system. And if you go to larger system for go-go, you can see that the difference between black and the red are relatively small so that you may not worry too much because most of the cells are in these wide regions. Yeah, so this is like numerically just say if it's violate these conditions, I reset the bulk pressure every time step to the maximum thermal pressure values. No, total pressure, yeah, total pressure is set to 0 in there effectively. Yeah. Yes. The systematic uncertainty is, I think, is varying different coefficients, the second order coefficients, like taking on and off the second order transport coefficients, etc. And also taking out the initial condition bulk and something. So there is also something you can vary using the conventional hydro theory by just varying the initial setup and see the variations. Yeah. But this may not be the reliable systematic check, but just say varying certain parameter in the setup to see the sensitivity to those observable in the small systems. Okay, so now we can go one step further. So the Georgian collaborators actually did more hard work, basically derived the 4 nonlinear causality conditions, including both shear and bulk. So here, basically, the green box are the necessary conditions. You have 6 of them, with basically the so-called inverse Reynolds number, say bulk over E plus P, or the lambda over E plus P. So lambda is the eigenvalue for the shear stress tensor. You can actually have the convention this way, and then you can actually write down all these components. So the first thing is to try to understand how we can, as a phenomenology practitioner, how to actually use these conditions. I think, there's also a condition for the sufficient condition, which is 8 of them. So we'll not talk too much on the sufficient condition, or mostly focus on the causality on the necessary conditions. So first is, this is work with the high school student their time and trying to kind of visualize what regions of the regions of allowed inverse Reynolds number. So in the shear and bulk sectors are actually allowed for bulk, for causalities. So basically, we define the shear inverse Reynolds number by the square root of pi mu over E plus P, and then the bulk in this way. So with different choice of the second order transport coefficients, the restricted one is usually kind of standard as the Israel-Stewart, where you don't have the extra additional second order terms. And also the DNMR has basically non-zero coefficients for these transport coefficients. And the causality regions and A-color region basically indicate these different colors in this 2D, two-dimensional plane. So you can see the red region is basically where the fluid cell will violate necessary conditions. And then the yellow region is a mixed zone because the causality condition not only depend on these 2 variables, but also depend on the speed of sound locally. So that depend on different value of speed of sound, in these regions, you might get causal or in-causal regions. In the green regions, you definitely get the causal regions. Causality satisfy the necessary conditions in these green regions. And then if you further go into smaller value like sufficient conditions, you get these dark blue regions. So one thing you find is that if you set this second order transport coefficient to 0, the positive side of the bulk inverse Reynolds is kind of unrestricted. You can artificially have really large say, positive bulk of E plus P and get the actually sufficient conditions satisfied in these regions. And adding these non-zero conditions actually constrain both value of the bulk in there. And then you can see that if you really want to be in this more comfortable zone in the sufficient regions, the only allowed value for shear and bulk is really small in this inverse Reynolds number about these values. That is only allowed for this hydro to be causal in this to valid sufficient conditions. And the necessary conditions in this green box in here. Yeah. Mm-hmm. I don't know what dominant energy condition is. Sorry. Yeah. 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 Then it should be around 1. So this yeah. So this should be around 1. So you just instead of pressure, you just add any density. Yeah. Mm-hmm. 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 Sure. Yeah. Sure. Yeah. Mm-hmm. 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 I see. Uh-huh. Yeah. But I think this will be also far in the red regions, probably. Oh my guess. Yeah. Yes. Yeah. Yeah. Mm-hmm. Yeah. Okay. So, but that's basically just a static analysis of George company's inequality conditions, and you can sort of get a feeling about what's the value of inverse Reynolds number defined this way needs to be, and if they are large, you will violate causalities. Yeah. This is not so. If you look at these conditions, there's no temperature in here, so it's basically this value, and then CS square. So CS square somewhere. So essentially, the band you see, the yellow band is essentially varying CS square from say 0.15 to 1/3. The yellow band for here. So yeah, so that's basically the uncertainty in there. So that's the mixed region, and the green region saying that for all value of CS squared, all the necessary conditions is valid. Yeah, for square is all valid. Yeah, it's all validates. Yeah, yeah. Okay, so that's basically give us some kind of intuition about George's inequalities, and then we can now just really check those N1 to N6 conditions in one hydrodynamic fluid simulation. So left-hand side show you 30 to 40% gold. For different colors, the histogram of the fluid cell with this value. So when the histogram hit these causality violating regions, which means those fluid cells are violating causality, violate the necessary conditions of causality, violating causality as well. So the right-hand side is the same histogram for the proton-gold collision in central. So you can see compared to this is that usually the number of histogram, number of fluid cell is actually a lot larger in this protonlet and then the gold for violating causalities. However, the issue is the hydro will run even with this violation observed, and no numerical instability was observed through these calculations, and we think this is mostly due to regulation. Lawrence, you may have some more insights from your work, now more towards to these directions. But that time was this was a little bit confusing to us because we see that this is a violation of causality, but there's no instability observed in the numerical simulations. Yeah. Sure, but yeah. Mm. Mhm. 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 Yeah, it could be the initial condition as you point out that you didn't do the time derivative for the Soster, and also it could be due to the actual every steps there's a numerical regulations when the inverse Reynolds numbers become too large. They could also stabilize the hydro and maybe go to some different trajectory for those cells. Yeah, those should be in these regions. Yeah, so that unstable, I don't know how to check, but yeah, should be possible to do if we know the condition. Yeah, so we can further discuss this. Yeah, yeah. Hmm. Yeah. Hmm. Yes. Yeah. So every time I count this, this is the accumulated ones. Yeah. Yeah, whole lifetime. Yeah, the full four-dimensional space. So yeah, so in our paper we wrote, this is actually quite small. I think about 3 or 4%. I don't, if I remember. Yeah, yeah. All the cells are violate causality. Yeah, above 3,000. Yes. Yeah, yeah. Yes. It's mainly on the edge and also early time. So once you go to after one Fermi, you will see that all of them have become quite reasonable. It's mostly violating the first Fermi over C. Yeah. Mm-hmm. Yes. So N6 is always the problematic one. So yeah, in efficiency that for example we find that the N2 and N4 always on the high side, never violates. So you may not even need to check them. But the code we code all 6 of them and then just to be safe. Yeah, yeah. It also depends on the choice of second order transport coefficients. I think some of. So N6 is this one. So yeah, yeah, yeah. So M5 and N6 can be actually combined. So one is bigger than 0, one is smaller than 1. So essentially, you can combine these two in a more compact form. Mm-hmm. Yeah, the linear causality condition is already there in this case. Yeah. Yeah. So because this one is the linear causality, and the choice with the choice we default have, this is already close to the boundary. So that's why adding the second two terms will violate the causality easily. Yes, yes. So there's one. Yeah, yeah. The answer is the positive ones. Yeah, bigger than 0. No, you need to look at the coefficients in front. This may not be positive, I think. Yeah. Yeah, so both yeah, so either so these two actually constraint coming hand in hand. Yeah. Yeah. Hmm. There are two of them, yeah. Yeah. So there are two of them. Some of the M4 has two of them in there. So but this one actually more well behaved usually in practice. Yeah. Yeah, the largest one, yes. Yeah. Yeah, yes. Yeah, yeah. Yeah, yeah. Yes, yes, yes. Hmm. Yeah. Hmm. 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 Worse. Hmm. Yeah. Hmm. Yeah. Hmm. Yeah. Hmm. Hmm. It could be some specific calculation. Yeah, some calculation could be. Yeah. Yeah. Yeah, I think it's probably this part, right? So you can just keep adding bulk to be positive and you can get all causal conditions. Yeah. 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 Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Okay. Okay, so now you can actually say, okay, so we've observed these causality violations. One of the easy fix is I impose a global constraints on the value of inverse Reynolds number numerically, so that I just look at this. So that essentially what this value imply is essentially saying that I need to make sure that the bulk and the value of this is smaller than the pressure. If I do this, I can find that all the fluids are not in the causal regions. They actually kind of, kind of not violating anymore. So this is kind of the first trial we do. We just reset the shear stress tensor and bulk by hand when they violate this inequality and set to this maximum value. And this is one way to basically say, okay, you can numerically regulate these causality violation cells. And we also find that if you use the different transport coefficients, like this linear pattern from the strongly coupled ends, the allowed value that is much more less restrictive, so you can relax the constraint to about 0.6 for the inverse Reynolds number. So this means that the choice of the transport coefficients or its functional form, really kind of important if you want to make systems causal in these conditions. So you can allow for a bigger value of this inverse Reynolds number if you choose a different bulk relaxation time in there. So then we basically go one step further. This is kind of now the working kind of in progress. So we still going back to look at those conditions and then find out, okay, we want to, instead of imposing a global constraints, we basically now code in these conditions in in the evolution of hydro. And then we can check those necessary conditions fluid by fluid cell, and then define a regulator alpha so that we can regulate the size of shear stress tensor and bulk stress tensor so that it makes sure that all the fluid cell kind of satisfy the necessary conditions. So that's kind of the local treatment compared to the previous global treatment of using some fixed ratios. So once these are done, you can see that this is basically a histogram of this alpha minimum. So alpha minimum equal to 1 means no regulation. Alpha equals 0 means very strong regulations. And then you can see that if you look at most of the regulations trigger is between the hydro starting time 0.4 and the first Fermi. So you see there's a tail of this regulation go to smaller value of alpha to regulate the initial stress, the shear and bulk part of the tensor at the first Fermi over C. And you can see those alpha factor shrinks significantly go to a later time. And then up to about 3 Fermi evolutions, all of them almost peak at the around 1, so you don't get any effective regulation anymore. So this is kind of consistent with the ULC group. We found that the violations mostly in the early time, so that we can basically in there. And then basically, you can use this alpha as a regulation scheme in the stack calculation, then simulate things by imposing the necessary conditional causality. Another way that we are working with Gabriel and Matt is that we define some kind of, redefine some value of shear viscosity so that this is kind of closer bound to the actual necessary conditions. We basically deduce these two values. And then you can rewrite the 6 necessary conditions into 2 using these R tilde variables. And then this is that once these 2 conditions are satisfied, you ensure all the 6 necessary conditions are also satisfied. This is a little bit more restrictive compared to the actual necessary condition. So in that case, we just need to deal with 2 inequality and make things a little bit easy to track. And then the N1 and N2 are basically these 2 expressions with these R tilde variables. So then we, instead of dealing with, say, 3 components of shear viscosity, 1 component of pi, we just deal with these 2 inverse Reynolds tensor in the evolutions. So the idea is that we noted that in order to satisfy the causality conditions, the N1 and N2 needs to be bound between 0 and some value like this. And then this means that if we can find the evolution equation for this two inverse Reynolds number to be bound by some maximum values, then we can impose this causality conditions numerically, and then we don't need to do any ad hoc numerical regulations, but the equation of motion will actually help us to ensure that the causality fulfill every steps. So this one that we look at the evolution equation of motion for the Shen-Bock tensor, and then we find that if we can introduce some regulation factor f, which depend on this arctangent of these two values, and then renormalize or redefine your transport coefficients in this way, then you can show that the evolution of this R tilde are bounded by this 1, 0, and 1 over alpha value, which alpha you can control as a numerical input parameters. And then in the small alpha limit, this f regulation function can be extended this order, and you can find that the additional terms you introduce to the transport coefficients only come into third order ingredients. That means that in the equilibrium or near equilibrium case, we're actually still solving the Israel-Stewart equations, but when we go to very far out of equilibrium where these are sizable, then the transport coefficients get renormalized by this f factor. And this allows us to have a bound value for the inverse Reynolds number. Yeah. In this case, yes, we try initially just to do the test on the transport coefficients, not very effective. But if you do the first order, it's much easier to control as well in there. So okay, so this is basically a numerical scheme, and then we can go ahead, and then we know that this inverse Reynolds number, yeah. Yes. No, so we just essentially put this f into the evolution of those equations. So then you just evolve fully in there. You can show that this never exceed the bounds anymore. Yeah. Mm-hmm. Yeah. Yeah. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. 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 Yeah, yes, yes. Right. So I think I quote your paper somewhere. Sorry, yeah. So you and George has, for bulky, I think that's also somewhere we inspired this approach with. But we just tried this for both Shen and bulk, and we found this is probably an easy way numerically we control. Like we can set the alpha to different values, and we control the maximal size of this inverse Reynolds number numerically, so that it could be useful to see this way. So okay, so with this constraint, you can actually see that if you take alpha equals 1 and pick some CS values, you will find that there is still a value in this phase space of this R tilde that valid causality in these red regions. But if you take alpha equals 1.5, you can show that all the regions of the phase space are satisfying necessary causality conditions. So this alpha equal 1.5 is basically the numerical value that we put in to basically consistent with the lattice EOS and the choice of transport coefficients. So you can now just solve this equation with this resum condition. So we compare several treatments. So standard is music, black is no treatment at all. If valid causality, the valid causality. And then red means that every steps we check this N6 causality condition. If it violates, we just reset the pi minute to be the maximum value allowed. So that's the red dashed line. And then the resummed transport coefficients is the green line, which will induce this arctangent factor to resum the equation motion for the shear stress tensor. So as you can see that for one lat collision in semi-peripheral, the energy evolutions look more or less the same. No difference. There's some difference in the late time. For the inverse Reynolds number for the shear, you do see that there are some difference in the first order Fermi over C. This is log scale. So this part is all first order Fermi over C, where you do see some difference between the different evolution scheme. But at a later time, you do see that all of them are kind of relaxed to the Navier-Stokes limit. Yeah. Yeah. So the y-axis is, for example, in this case, the three curve on the top is the shear inverse Reynolds number in one fluid cell. At the x equals to 1, y equals. Yeah, we fix one cell and then look at the value. And then these three lines are the bulk inverse Reynolds at that fixed cell in there. Yeah. Then you can argue what's the influence at the end to the observables. So we look at the say go-go collision, lat collisions for a few different initial setup. So this one just say I initialize the system with ideal T mu, all the bulk and shear are 0 in the initial time. And you do see that for the observables that are usually used in the Bayesian calibration, particle yield, mean PT, and V2, V3, all three different conditions are quite close to each other. And this means that the system by itself initially are kind of not violating causality so that the constraints are not that big. And if you include about initial condition about 0.5 value of the value of the shear stress tensor, you start to see difference in the very peripheral collisions in there. But these two, both, sorry, oops. I'm not sure. I think you probably just switch here. Yeah. Am I still sharing? Or maybe my Zoom already fall off. I share again. Okay. Yeah, somehow I think the Zoom. Yeah, okay. Anyway, so this is about 0.5. So 0 and 0.5 are basically, because in this case, we need to make sure that the inverse Reynolds number are bound in this 0 and 1 over alpha, with alpha equal to 1.5. If you start with a value that is bigger than this one, then this equation motion will blow up because f is infinity, and we need to do regulation with this. So both these two cases are basically ensure that even at the initial step, this condition actually satisfy. And you can show that even with this one, the effects to the system of final state observables are quite minimal. And you do see that when you go to the equity of the four initial state using from this IP Glasma, where you do violate this condition in certain cell at the initial time. I need to do violation. I need to do some kind of regulations for initial steps. You do see there is a more sizable difference in mean PT, also V2, V3 in these peripheral collisions. So this means that if you want to do a Bayesian analysis and taking into account uncertainty from this treatment, you probably better to focus on the large system and central or up to semi-peripheral centralities to avoid variations from this due to different regulation schemes. So that's basically our numerical framework and my conclusion. So basically, causality bound condition can give us some upper bound of allowed viscous stress tensor when we kind of match the pre-equilibrium state to the hydro. And then this condition is kind of sensitive to what transport value you use for the second order transport coefficients. And then we develop several numerical methods, now try to incorporate these necessary conditions into the framework and try to estimate the theoretical uncertainty caused by them. The one that I show you is the lat, which is the most optimistic case, where the largest heavy ion systems. When you go to small systems, this variation will be more sizable. And that also poses the word that if you want to incorporate those small systems into Bayesian framework, that could be also challenging in the near future when you might want to have more kind of a robust formula, for example, these maximal entropy hydros that propose later that can help you to understand the theoretical uncertainties. That's all I have. Thanks. Mm, mm, mhm, mhm,
So we already had questions, but
mhm,
we have more time. Yes.
mhm. Yes. Mhm. You mean third order or further? Or do you mean, or different choice of the model? Mhm. Yeah, but I think if you want to look at the sensitivity to second order transport coefficients, mostly will show up in this small system like PLED, PA, or oxygen, or these smaller systems. For large system, we find it's mainly controlled by the shear viscosity and ball viscosity. So that's yeah. So but yeah. So it depends on the system size in terms of how much difference it will cause in there. Yeah. Yeah. Set to zero, right? Mm-hmm. Mm-hmm. Yeah, sure. Yes. Yeah, yeah. So in principle, you can do the analysis in there. Yes. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. It's a guidance. It's a guidance. Yeah, yeah. But even that, you can see that including non-zero values, you do get more stable picture, more physical picture about the causality zoom, right? So I would trust this zoom. Sorry. I'll trust this better than this one. Right? If you set to zero, these are unbounded. And this one actually, if you just put in some non-zero value, these are already bound, which is already quite good in there. Yeah. Mm-hmm. Mm-hmm. Sure, sure. Yes. Mm-hmm. 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 Yeah, to change them. Very, yeah, yeah, yeah. Okay.
Yeah,
Yeah,
but then, okay.
yeah, yeah,
Yes, Chung.
yeah, yeah.
Chung,
Yeah.
yes, please. You know, you raised your hand.
Yeah. Yes. We can apply this. We can compute. Yeah. So the question is, do you trust the calculation, right? We can always compute. And do you trust the numerical result with 100% confidence or 95% confidence? So my confidence of looking at the flow result go to small systems, the confidence level shrinks compared to the high level, like a Bayesian per people, right? So you should assign more theoretical uncertainty when you look at smaller systems analysis simulations, for example. Yeah. Yeah. Mm-hmm. Yeah, yeah. With the parameterization. Yes. Mm-hmm. 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 Yes. Yes. That's the usual approach by Gabriel to the minimal thing that we can use as to simulate, right? Yeah. Yeah. Yes. Yes. One can try. Yeah. Yeah, we already, so if you use the holographic form of the Bok-Tao pi, things become better in the choice, right? The causal one become a little bit less demanding. Mhm. Yeah. I think that's a Chodorong, his the talk. Maybe we can wait for him. Yeah, yeah. I think this week, right? Yeah.
Okay. What do you mean by maximum entropy method?
I think there's a maximum entropy method to derive the equation of motion of hydro, and sort of including some resummed terms in there. using maximum
looking
entropy.
forward to it.
Yeah. So it shows, yeah, Chandra draws, yeah, talk.
There are more questions I have. Oh, so there is a question. So,
Yeah. Yeah. Mhm. Mhm. Mhm.
I have one very naive
Sure.
question.
Yeah.
So, in relativistic hydro, I was, I always thought that the viscous correction of the pi, this capital pi or big pi should be smaller than the local equilibrium pi.
Yes.
So this was my prejudice. I don't know if this is a prejudice, but I can ask some questions to Gabriel as well. So, but in fact, you find that it's not that small. I mean, it's
In the simulation,
it exceeds, the
yeah.
ratio exceeds one.
Right.
So, the question is very simple. Does it make sense, or we're
Yeah.
outside?
So the question,
relativistic hydro?
yeah. So in the hydro equation, yes, but in practical, like simulation, if you want to simulate heavy ions, you need to introduce kind of numerical regulator when you deal with
this. I
this.
understand, but
Yeah.
from the point of view of the fact that the relativistic hydro applies, we claim
Right.
that the relativistic hydro applies to heavy ions.
So I think
we have some
to me,
functional cells where this ratio is larger than one. Therefore, this is no
Yeah.
longer a correction. This is just.
I agree. So I think you need to see kind of how much fraction it happens in the actual simulations and how much influence to the final observer. It's the final observer is still dominated by the correct hydro response in the bulk. Then I think still hydro should works. But I agree. So it's kind of not a 1 to 0 option, but yeah, it's
If we
deviant.
go to PP for it.
Yeah, it's more and more challenging. It's yeah.
We have two more questions. I don't remember the order.
Yeah. Mhm. Mhm.
We definitely know examples where you talk about microscopic theory, and the hydrodynamic theories are a good description, even when the corrections are not small. So for TCD, the larger the correction, the less confidence you should have. But there's no point where you can say like, I definitely shouldn't be valid here or here.
No, but valid causality, I would say it's probably break down. Something should break down. Some. Yes. Yeah.
It's hard to say exactly.
Yeah. Mm-hmm.
It's hard to say like, okay,
Mm-hmm.
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 It's not really clear exactly what that's
Mm-hmm.
in many cases, like very, very far from equilibrium, and we know how it works.
Mm-hmm.
So it's hard to say. So at least for me, this is why I think the causality analysis is very much more definitely. I broke up the causality, therefore, at least it's
Mm-hmm.
Okay, yeah, Rajiv and then again.
Mm-hmm. Mm-hmm. Yeah. Well, you will see more uncertainty. I would say you will see more uncertain theory and intrinsic uncertainty in the calculation that haven't been explored. If you do see that there's some observable sensitive second order, the choice of second order transport coefficients, right now I will see that as a theory uncertainty yet, but not the opportunity to constrain them using data yet.
so yeah, just to make a comment. Already on Earth,
Mhm.
those are not described by anything like Navier. They are described as, basically people what they do, they put on the x-axis sigma mu, on the y-axis pi mu, and they measure, get some sort of weird functional, non-linear functional dependencies. Some space power laws in ketchup. Pi mu is like sigma mu to the power 0.1. It's not even linear. I mean, there is some linear relationship, I think, infinitesimal gradients, but you never see that. Right? So I don't think we can claim that when pi is of the order of the threshold, hydrodynamics is what our theory brain says, small deviations from equilibrium, small corrections, small gradient expansion effective theory. From what I see, what we're doing here is just finding some way to close the system of PDEs, right? We have a collection of conservation laws, deducing mu equals 0. We have more components than 4, right? These are 4 equations, but we have more components than 4. We invent something that we hope will kind of fit the behavior, but the justification for hydro has completely gone away, right? Because we already know so many substances where, P is still very, pi mu is still much smaller than P, but we cannot use anything that looks like Navier-Stokes or reference keyword in those stuff. So, yeah, I would say we're still far away from having a clear answer to this question. Does it make sense, right? We're trying to, we have some microscopic theories, we have some attractors, we fit the theory in the attractors, we try to see if they look kind of the same, but yeah, there is no clear foundation.
I wanted to add that Professor said that this theory is valuable. And then we look at the dynamic theory, and you read it,
yeah, that's my direction. My plan is to do something of that kind with problems, which is more or less similar to the idea you're already having.
Yeah, go ahead. Yeah, this is not in there yet. Still challenging, very challenging one. I agree. That's a very challenging topic of if you do numerically, I think that expert is on next to you. So yeah, so we can probably. This is not including there yet. Yeah.